4 months ago, this comet did not exist in any catalogue. Today, it is the most interesting thing in the solar system, and you have exactly 47 hours before the moment passes. Right now, Comet PANSTARRS is burning through perihelion inside Mercury's orbit, and its ion tail is threading outward, straight across Earth's orbital path. Our planet is walking into it, quietly, invisibly, on a clock nobody set. Meanwhile, a high-speed stream of solar wind is already en route from a coronal hole. A sunspot with complex and unstable magnetic structure is facing directly toward us, and the Japan Trench is still working through the aftershock sequence of Monday's magnitude 7.4. None of these events are related, but stick around because their convergence on the same 48-hour window is exactly where this story is. If this already has you thinking, hit like and subscribe to the Skylab. This story has layers we have not even opened yet, and you will want to be here when more data streams in. Now, let us get into it. Part 1. The claim nobody can verify yet. 47 hours from now, Earth is going to walk through something. Not a meteor shower, not a solar flare, not anything you can see with your eyes or feel in your bones or read about in any emergency alert. What is coming, or more precisely, what Earth is drifting toward, is a faint, magnetically threaded ribbon of ionized gas stretching hundreds of millions of kilometers across interplanetary space. It belongs to a comet most people have never heard of, and the question of whether we will actually be able to detect it when it arrives is, honestly, one of the most interesting problems in heliophysics right now. Not because it is dangerous, it is not. Not because it is visible, you will not see a thing. But because it sits at the exact intersection of rare geometry, bad timing, and the fundamental limits of what our instruments can actually measure. Let us start with the comet. Comet C/2025 R3, designated PANSTARRS, was discovered only a few months ago. It is what astronomers call a long-period comet, meaning it comes from the outer reaches of the solar system, somewhere in the cold, dark territory beyond Neptune, possibly from the Oort cloud itself, and it swings inward toward the Sun on an orbital arc that takes thousands, possibly tens of thousands of years to complete. This is likely its first close encounter with the inner solar system, which makes it scientifically interesting for reasons we will get into. But what makes it relevant right now on this specific week is where it is in its orbit and where its tail is pointing. As of this recording, PANSTARRS is making its closest approach to the Sun, its perihelion, inside Mercury's orbit. That is extremely close. The heat and radiation at that distance are intense enough to drive enormous outgassing from the comet's nucleus, liberating frozen volatiles, ionizing them almost immediately and sending a stream of charged particles flowing away from the Sun along the solar wind. That stream is the ion tail, and right now, that ion tail is pointing almost directly at Earth's orbital track. Here is what needs to be understood immediately, because this is where the language can get slippery. Earth is not going to collide with a comet. The comet is nowhere near Earth. The comet's nucleus is currently inside Mercury's orbit, closer to the Sun than any of the inner planets. What Earth is doing is crossing the line, the geometric projection of where the tail extends outward. Think of the comet as a fire hose pointed roughly in Earth's direction. The water from that hose is the plasma, and it has been spraying in our direction for weeks. Earth is about to walk through the spray zone, not the nozzle. And the spray, by the time it reaches us, is extraordinarily diffuse. We're talking about particle densities that are comparable to, and in some regions probably even lower than, the already thin solar wind that surrounds us constantly. So why does any of this matter? Because in science, rare geometries are data. And this particular geometry, a planet sweeping through the projected ion tail of an active comet, almost never happens in a configuration where we have the instruments in position to measure it. The alignment window is narrow, April 24th through 26th, roughly 48 to 60 hours during which Earth's orbital motion carries it across the projected path of the tail. After that, the geometry closes, the window disappears, and if we did not capture anything useful during that window, we will not get another chance with this comet for potentially thousands of years. Now, to be clear about what detection means here. We are not talking about some dramatic event that shows up on dashboards and triggers alerts. We are talking about the possibility of a subtle but scientifically meaningful signal appearing in spacecraft data, a slight rotation of the interplanetary magnetic field, a faint spike in heavy ion concentrations, a barely measurable drop in proton density. Exactly the kind of signal the Ulysses spacecraft accidentally recorded when it crossed Comet Hyakutaki's tail in 1996, a discovery that was not even recognized until the year 2000. We will come back to Hyakutake, because that story is crucial. The complication, and this is where worst possible moment starts to mean something, is that Earth is entering this detection window during one of the more active stretches of space weather we have seen in recent weeks. Solar wind speed is elevated, electron flux has been running high for multiple days, a magnetically complex sunspot region has developed on the Sun's Earth-facing disk, and a high-speed stream of solar wind from a coronal hole is forecast to arrive right around April 24th. The same 48 hours when we need the data to be as clean and quiet as possible is shaping up to be exactly the opposite. That is the core problem. Not whether the tail is there, not whether Earth crosses it, but whether, given everything else that is happening simultaneously, our instruments can actually distinguish the comet's faint fingerprint from the roaring background noise of an irritable sun. The signal exists in theory. Whether we can hear it is another question entirely, and as we go through everything converging on this window, you will start to understand why some scientists who look at data like this will tell you quietly that most tail crossings are never confirmed at all. They happen, they pass, and the data sits unexamined until someone years later notices something strange and goes back to check the calendar. We are in that calendar right now. Part 2. Geometry as destiny, but also misleading. The first thing you need to understand about a comet's ion tail is that it does not trail behind the comet the way a wedding veil trails behind a bride. This is one of the most persistent misconceptions in popular astronomy, and it matters enormously for understanding why this detection problem is so hard. A comet's ion tail, also called the plasma tail, is pushed directly away from the Sun by solar wind pressure and the interplanetary magnetic field, always, regardless of which direction the comet is moving. So if the comet is heading toward the Sun, as PANSTARRS is near perihelion, its ion tail is actually pointing forward relative to its direction of travel, outward, away from the Sun toward the outer solar system. The tail is not a contrail, it is a weather vane. It always points anti-sunward, pushed by the continuous outflow of charged particles streaming away from our star. This has a significant implication. The geometry of which planet or spacecraft might cross that tail depends entirely on where the tail is pointing, which depends on the Sun-Comet line, which changes as the comet moves along its orbit. And because PANSTARRS is currently interior to Mercury's orbit, inside it, closer to the Sun, the anti-sunward direction from its position happens to be roughly aligned with Earth's current location in space. Not exactly. These alignments are never exact. But close enough that models suggest Earth's orbital path will sweep through the projected tail region during that April 24th through 26th window. Now here is where the geometry becomes misleading and where you have to be careful about what the word crossing actually implies. The tail is not a solid object. It is not even a continuous structure. It is a magnetically shaped, constantly shifting ribbon of ionized molecules, things like water ions, carbon monoxide ions, the kind of molecular fragments you get when solar radiation tears apart the volatile compounds outgassing from the comet's nucleus. At the comet's head, near perihelion, this material is dense enough to be spectacular, but by the time it extends outward half an astronomical unit or 1 astronomical unit, the density has dropped dramatically. The tail becomes gossamer, transparent, a structure that exists more as a magnetic pattern than as a tangible concentration of matter. The solar wind further complicates this. As the solar wind pushes and twists the interplanetary magnetic field, it distorts the shape of the tail in real time. The tail does not hold a fixed shape the way a river holds its banks. It writhes, it kinks, it can develop disconnection events, large sections physically breaking off and drifting away, triggered by sudden changes in solar wind conditions, and it constantly flickers and restructures as new material streams away from the nucleus, and old material gets diluted and absorbed into the background plasma flow. This is the crux of what scientists call the probability versus detectability gap. The probability that Earth is geometrically crossing the projected path of PANSTARRS' tail during this window is actually relatively high. The orbital math puts us in the right zone. but the probability that the tail still has coherent detectable structure at Earth's position, in the form that instruments can unambiguously identify, is a completely different question. And the answer to that second question is much more uncertain. Here is a useful way to think about it. Imagine a long road that was briefly covered in snow a week ago. The snow has since been partly blown away by wind, partially melted, partly refrozen in strange patterns. You can still find traces of where the snow was if you know exactly where to look and if the conditions are right. But if someone asks you whether the road is snowy right now, the honest answer is probably something like, maybe in patches if you look carefully. The comet's tail at Earth's distance is something like that road. The material is there, or was there, or some of it is there somewhere in that spatial zone. Whether Earth sweeps through a coherent enough patch to leave a measurable imprint is genuinely unknown. What we do know is that no real-time mapping of tail density at Earth's position is possible. We cannot see the tail the way you might see a weather system on a radar map. We cannot send a probe to check the density gradient before Earth arrives. The only way to know what is at Earth's position is to be at Earth's position and measure it, which is exactly what the spacecraft at the Lagrange 1 point and elsewhere will be doing during the window. The modelling limitations here are worth dwelling on for a moment because they are fundamental. The models that predict where the tail will be and how dense it will be are built on assumptions about solar wind conditions, the comet's outgassing rate, the magnetic field geometry, and dozens of other variables, all of which carry uncertainty. Small errors in any of these inputs can translate into large errors in the predicted tail location and density. Scientists can say, the tail should be in roughly this region, but they cannot say the tail will be dense enough to detect at this exact time. And even if the alignment is geometrically perfect, the physics may produce no clear signal. That is perhaps the most counterintuitive point here. A perfect geometric crossing does not guarantee a measurable event. Whether something is measurable depends entirely on whether the signal clears the noise floor, and right now, as we are about to get into, the noise floor is not cooperating. Part 3. The precedent that was missed. In May of 1996, the Ulysses spacecraft was minding its own business on a high-latitude trajectory through the solar system when something strange showed up in its data. The interplanetary magnetic field made a sharp rotation, proton density dropped by roughly a factor of 2, and the ion composition sensors registered the presence of heavy ions, oxygen, carbon at concentrations that did not match the usual solar wind background. Nobody noticed at the time. The data was recorded, archived, filed away with everything else, and Ulysses continued on its mission. It was not until the year 2000, 4 years later, that a team of researchers pulled the 1996 data, compared it to Comet Hyakutake orbital trajectory, and realized what had happened. Ulysses had crossed Hyakutake's ion tail. Not near the comet, not anywhere close to the comet. The crossing had occurred at 3.8 astronomical units from the nucleus, roughly 360 million miles away. The tail had extended that far. The signal, once someone knew what to look for, was unmistakable in hindsight. This is the historical precedent that makes the PANSTARRS window scientifically significant. It is proof that comet ion tails can maintain detectable structure over extraordinary distances. It is proof that spacecraft can record real, measurable signatures when they cross those tails. And it is proof, perhaps most importantly for this story, that those signatures can be buried in the data for years before anyone goes looking. Let us go through what made the Hyakutake detection scientifically clean, and then contrast it with what Earth faces this week. Ulysses was a single spacecraft in a relatively uncrowded, quiet stretch of interplanetary space. The background solar wind conditions at that location were relatively stable. There was no concurrent coronal hole high-speed stream complicating the magnetic field geometry. There was no elevated electron flux muddying the ion composition data. The spacecraft was not embedded in a planetary magnetosphere that introduces its own layers of interference. It was just sitting there, in the solar wind, doing its job, and the tail passed through. The signal itself had 3 distinct components. First, the magnetic field rotation. The interplanetary magnetic field changed direction sharply at the boundary of the tail, a signature of the magnetic draping that occurs when solar wind field lines wrap around the material outgassing from the nucleus and stretch backward into the tail. Second, the density drop. Inside the tail, proton density fell, consistent with a region where the cometary plasma partially displaces the normal solar wind. Third, the heavy ion detections, oxygen and carbon ions appearing at concentrations above the background, direct chemical fingerprints of cometary material. These three things together made the case bulletproof, even 4 years after the fact. No individual component was definitive on its own. The magnetic rotation could have been a solar wind discontinuity. The density drop could have been a quiet sector passage. The heavy ions could have been trace contamination from various sources, but all three together, aligned in time, along a trajectory that could be projected back to Hyakutake. That was a tail crossing. Now here is the critical difference. Earth this week is not Ulysses in a quiet stretch of interplanetary space. Earth is a planet with a magnetosphere. Earth has a fleet of spacecraft monitoring it, but those spacecraft are operating in an environment that is already magnetically complex, already seeing elevated particle fluxes, already about to be hit by a coronal hole high-speed stream. The very signatures that made Hyakutake's tail identifiable, the magnetic rotation, the density drop, the heavy ions, are exactly the kinds of features that solar wind disturbances produce on their own, independently, without any comet involved. This is the detection challenge in its sharpest form. Not is there a signal, but can we distinguish the signal from everything else that looks like it? And the deeper, more unsettling implication is this. Even if we cannot answer that question now, even if the April 24th through 26th data comes back ambiguous or overwhelmed by solar noise, that does not mean nothing happened. It may just mean we are living the beginning of a Hyakutake story. The data will be archived. Someone will look at it in 2 or 3 or 5 years, and they may find exactly what we are looking for, or they may not. Both outcomes are scientifically informative. Both require the data to be carefully preserved. But right now, with 47 hours on the clock, the immediate question is whether anyone will notice anything at all. And for that, we need to talk about the noise. Part 4. The first complication. This isn't a quiet background. Before we even get to the sunspot and the coronal hole, and those are coming, believe me, it is worth establishing what the baseline space weather environment looks like right now, on its own terms, separate from any extreme activity. Because even the ordinary background conditions at this moment are not what scientists would consider favourable for sensitive detection work. Solar wind speed has been running above 500 km per second for the past several days. To put that in perspective, average solar wind speed is somewhere around 400 to 450 km per second, give or take. 500 plus is elevated but not dramatic. It is the difference between a steady breeze and a stiff wind. In practical terms, it means the magnetic field environment at Earth's position is more dynamic, more variable, and more prone to short-term fluctuations that can look like anomalies if you are not accounting for them carefully. Electron flux, meanwhile, has been running at high levels for multiple consecutive days. Elevated electron flux is partly a consequence of elevated solar activity, and partly a function of the geomagnetic conditions. It tends to build up during active periods and can take days to decay back to baseline even after the driving conditions settle down. For instrument operators, sustained high electron flux is a quality of data concern. It contributes to background noise in certain measurements, and it can interact with spacecraft in ways that introduce systematic errors into datasets, if not carefully corrected. Now add to this the geomagnetic conditions. Geomagnetic activity, measured by the KP index, which runs from 0, meaning completely quiet, to 9, meaning the most extreme storms, has been hovering in the quiet to unsettled range, with occasional upticks toward active. This is actually fairly typical for this phase of the solar cycle, but it is worth noting because it means Earth's magnetosphere is not in a pristine dormant state. It is mildly excited, jostled by the ongoing elevated solar wind. And a mildly excited magnetosphere means more baseline variability in the measurements taken by spacecraft in the near-Earth environment. Here is the fundamental problem this creates for the detection question at the centre of everything we are discussing. Instruments do not detect events, they detect changes. Specifically, they detect changes that are large enough relative to the ambient variability to be statistically distinguishable from noise. If the background is stable and quiet, a small signal stands out clearly. If the background is already variable, already flickering with the signatures of elevated solar wind, fluctuating electron flux, mild geomagnetic activity, then a small signal gets buried. It does not disappear from the data. It is still there, mathematically. But it is hidden under the noise floor, and extracting it requires statistical methods that introduce their own uncertainties. A useful analogy: imagine you're trying to hear someone whispering your name across a crowded room. If the room is silent, you might catch it at 10 meters. If the room has a dozen conversations going, ambient music, and someone occasionally dropping something heavy, you might miss it at 3 meters. The whisper is still there. The sound waves are still arriving at your ears, but the signal-to-noise ratio has fallen below the threshold where your brain can reliably pick it out. That is approximately the situation our spacecraft are walking into. The comet tail signal, if it is there, is the whisper. The current space weather environment is the noise in the room. And right now, before the coronal hole stream even arrives, the room is already not quiet. The particularly tricky part is what scientists call false positives. Solar wind fluctuations are not random in the same way that background electronic noise is random. They have structure. They come with magnetic field rotations, with density changes, with composition variations caused by different solar source regions. All of these structured fluctuations can, by coincidence, look like what a comet tail crossing would look like. A sudden IMF rotation that has nothing to do with any comet. A density decrease caused by a transient quiet sector in the solar wind. Trace heavy ions from a solar energetic particle event. Each of these, in isolation or in combination, could be misread as a tail signature by someone who wanted to see one. And conversely, this is the part that keeps scientists honest. A real tail signal could be dismissed as a solar wind fluctuation by someone who did not know it was there. That is exactly what happened with Hyakutake for 4 years. The data will need to be filtered, corrected. Compared with models of the background solar wind, cross-checked against multiple instruments and multiple spacecraft. That process takes months, not hours, which means the answer to the question, did we detect PANSTARRS' tail, will not come in a press release on April 26th. It will come, if it comes at all, from a careful paper, probably published a year or more from now, by a team that spent months arguing over how to separate the signal from everything else. That is assuming the Sun cooperates at all. It is about to do the opposite. Part 5. The sunspot that arrived right on time. Something has been growing on the Sun's face. It started as a modest cluster of magnetic disturbance a few days ago, but it has been developing steadily, and as of this recording it has earned a classification that space weather forecasters pay close attention to. Active region 4420, catalogued with a beta-gamma magnetic configuration. That classification matters. Sunspot regions are categorized by the complexity of their magnetic topology, the way north and south polarity fields are arranged relative to each other. A simple alpha or beta configuration means the opposing polarities are reasonably well separated, relatively stable, unlikely to suddenly reconnect and release large amounts of energy. A beta-gamma configuration means the polarities are mixed together, tangled at their boundaries, with the kind of topological stress that makes magnetic reconnection and the explosive events it causes much more probable. Active region 4420 has grown to roughly 180 millionths of a solar hemisphere in area, which is substantial but not record-breaking. It contains about 15 individual sunspot umbra, spread across a configuration that has been described by forecasters as magnetically complex and continuing to evolve. Flare probabilities have been running at around 75% for C-class events over any given 24-hour period. Those are moderate flares, and around 10% for M-class events, which are larger and more energetic. An M-class flare from a well-positioned active region is the kind of event that produces measurable effects at Earth: elevated proton fluxes, increased ionospheric absorption, possible geomagnetic activity if it comes with a coronal mass ejection. Now, to be clear about the current threat assessment, as of this recording, no major Earth-directed coronal mass ejections have been observed from AR 4420. The region has been active but has not yet produced the kind of eruption that would send a significant plasma cloud directly at Earth. Flares are generating X-ray bursts that are affecting high-frequency radio propagation. That is a routine consequence of moderate flaring, but the more dramatic scenarios, the ones that would fundamentally change the space weather situation for the next several days, have not yet materialized. But the operative word there is yet. And here is where AR 4420 connects back to the question of PANSTARRS tail detection. Even without a major CME, an active sunspot region constantly perturbs the solar magnetic topology. It generates outflows of energetic particles. It creates variations in the solar wind emanating from regions near it. It introduces complexity into the interplanetary magnetic field, the same magnetic field that the comet's tail is threaded through, the same field whose rotational signatures would be one of the primary detection indicators. Think of it this way. The interplanetary magnetic field is the fabric of interplanetary space. The comet's tail leaves patterns in that fabric, wrinkles, distortions, magnetic draping structures that spacecraft can measure. But an active sunspot region is constantly sending new ripples across the same fabric. Those ripples do not cancel out the comet's patterns, they overlap them, they mix with them. And from the instrument's perspective, an overlapping ripple from an active region looks almost identical, in kind, if not necessarily in magnitude, to the patterns a comet tail would leave. This is the detection problem from the solar noise side. The sun is not deliberately trying to hide the comet's tail from us, it is just being the sun. But the consequence is the same: a higher noise floor, a more complex magnetic environment, and a harder job for the scientists who will eventually sit down with the data and try to find something unusual inside it. The situation would be challenging enough with just the active region in play. But AR 4420 is not the only complication arriving this week. Something else is on its way, and its timing is, frankly, almost absurdly inconvenient. Part 6. The coronal hole that changes everything. On the sun's surface, or rather, in the corona above it, there is a region where the magnetic field lines do not close back into the sun the way they normally do. Instead, they stretch outward, open to space, and allow solar material to stream freely along them into the heliosphere. These regions appear darker in extreme ultraviolet and X-ray imaging, hence the name coronal holes. And the solar wind that pours out of them is different from the ordinary background solar wind. It is faster, it is less dense, and it carries a different magnetic field orientation. A fast stream emerging from a coronal hole does not just barrel through the solar system unimpeded. When it catches up to the slower solar wind that left the sun earlier, and it will, because speed differences in the solar wind do eventually result in overtaking, it piles up at the boundary between the fast and slow streams. This creates what is called a corrotating interaction region, or CIR, a compressed turbulent zone of enhanced magnetic field and elevated particle densities that sweeps past Earth with the rotation of the sun, roughly every 27 days. CIRs are effective drivers of geomagnetic activity, not as dramatic as a direct CME impact, but persistent, capable of driving multi-day elevated KP conditions, and, critically, magnetically complex in ways that are difficult to model in detail. The coronal hole responsible for the current stream has been tracked for several days, and its associated high-speed stream is forecast to arrive at Earth around April 24th. The same day the PANSTARRS tail-crossing window opens. Expected solar wind speeds in the stream, 600 to 700 km per second. That is a significant jump from the already elevated 500 km per second background. Expected geomagnetic effects, KP 4 to 5. That corresponds to active to minor storm conditions, enough to produce some aurora at higher latitudes, enough to increase drag on low-orbit satellites, and enough to fundamentally restructure the magnetic environment at Earth's position in ways that will absolutely show up in spacecraft data. The interaction between a coronal hole high-speed stream and the comet tail detection problem is layered. On one level, the arrival of fast solar wind changes the magnetic field orientation at Earth in ways that can be dramatic and rapid, exactly the kind of change that would normally flag as an anomaly worth investigating. If a scientist sees a sharp IMF rotation in data from April 24th and does not know about the CHHSS arrival, they might initially think comet tail, but the answer in most cases will be coronal hole boundary crossing. On another level, the increased turbulence in the solar wind during a CHHSS passage actually makes the comet tail's own structure less coherent. Remember that the tail is shaped and maintained by the solar wind. It is the solar wind that pushes the ions away from the nucleus and drapes the magnetic field around the cometary material. A sudden increase in solar wind speed and a change in its magnetic geometry will distort the tail. Fast wind from a coronal hole may accelerate parts of the tail, stretch some regions, compress others. The coherent magnetic draping signature that Ulysses detected at Hyakutake depends on a relatively stable solar wind carrying the tail structure intact across interplanetary space. A coronal hole stream is not that. There is a paradox buried in all of this that is worth acknowledging directly, because it is the kind of thing that makes space weather science genuinely interesting, rather than just frustrating. More solar activity means more particles, more magnetic field structure, more data richness in general. In that sense, a high-speed stream arriving during the window could in theory enhance some detection scenarios, specifically ones where the interaction between solar wind and cometary material produces secondary effects that would not occur in a quiet wind. The collision between fast solar wind and cometary ions might produce its own particle signature, something like the boundary effects at a CIR but weaker and chemically distinct. But this enhanced activity also introduces vastly more noise. It is the observational paradox in miniature. The events that most excite the space weather environment are the ones that make subtle signals hardest to extract. And right now, the coronal hole stream is not just adding noise to the detection problem. It is the dominant signal in the data, arriving precisely when we need the signal-to-noise ratio to be as favourable as possible. The geomagnetic effects on Earth's surface during a KP45 event are generally minor in practical terms. Some radio disruption, some satellite operational concerns, maybe a weak aurora for people at around 50 degrees latitude or higher. But for the spacecraft collecting the data that might eventually tell us whether PANSTARRS' tail left any trace, those conditions represent a significant analytical burden. Every measurement will need to be corrected for the background CHHSS signature before anyone can even start looking for something smaller underneath it. The window is narrowing, the noise floor is rising, and the signal we are hunting is not getting any stronger. Part 7. Plasma-on-plasma interference. Here is a thing that is easy to overlook when thinking about comet tail detection. The material in the tail is not exotic. It is not radioactive. It is not some alien substance that screams its presence in every dataset. It is ionized gas, molecules that have been stripped of electrons by solar radiation, turned into charged particles that can interact with magnetic fields, water ions, carbon monoxide ions, carbon dioxide ions, maybe some heavier molecules depending on the composition of the nucleus. These are not dramatically different from what the solar wind already contains. The solar wind is itself a plasma, mostly protons and electrons, with a smattering of helium nuclei and trace amounts of heavier ions. The boundary between solar wind and cometary plasma is not a sharp line with a flashing sign. It is a gradient, a place where the ratio of cometary ions to solar wind ions slowly changes as you move through the tail structure. And detecting that gradient requires instruments that can measure ion composition with enough precision and stability to notice that the ratio has shifted slightly, that there is, say, a slight excess of oxygen ions, or a slightly elevated concentration of carbon-bearing molecules compared to what pure solar wind background would contain. The problem is that the solar wind already contains trace amounts of heavy ions. Oxygen is present, carbon is present, silicon, iron, and other elements are present in small quantities, because the solar wind carries material from the entire solar corona, and the corona is not made of pure hydrogen. The ratios of these elements in the solar wind vary depending on which solar source region the wind came from, what the coronal temperature was in that region, whether there was any recent flare activity, and a dozen other factors. Those ratios fluctuate over timescales of hours, which means that looking for slightly elevated oxygen as a comet signature requires knowing, with some precision, what normal oxygen was in the same wind parcel at the same time. During a coronal hole high-speed stream passage, the ion composition of the solar wind changes characteristically. The fast wind from coronal holes has a different elemental fractionation pattern than the slow wind. It tends to have different oxygen charge state ratios, different iron to oxygen abundance patterns. These changes are well documented and can in principle be modelled out of the dataset, but they add a layer of complexity to the analysis that is not trivial. A comet tail signal sitting on top of a CHHSS compositional change is like trying to taste a specific spice in a dish that has already been dramatically changed by a completely different set of seasoning. The original flavour, if it is there, is overlaid, mixed, partially masked. An experienced palette with the right analytical framework can still extract it. But the uncertainty in the extraction is much higher. The concern about signal absorption is real here. Not absorption in the physical sense, the cometary plasma does not get destroyed by the solar wind encounter, but in the data sense, the signature of the tail's presence may become indistinguishable from the normal variation of the background. Not because the signal is too small in absolute terms necessarily, but because the background variability during this period is large enough to encompass the signal's magnitude. The signal falls within the error bars of the noise. There is also the specific concern about interplanetary magnetic field discontinuities. The solar wind is not smoothly flowing like water from a tap. It contains current sheets, thin boundaries between regions of different magnetic polarity, and various types of discontinuities where the field direction, speed, or density changes abruptly. These discontinuities are a normal feature of the solar wind and happen regularly, every few hours at Earth's position. Some of them are caused by stream interaction regions, some by variations in the source regions on the Sun, some by instabilities that develop in the wind itself during propagation. Here is the uncomfortable truth about these discontinuities. Some of them look, in their magnetic signatures, quite similar to what a comet tail boundary would look like. A sharp rotation of the field vector, a change in density, maybe even a compositional hint if it coincides with a different source region. The Hyakutake crossing, for comparison, involved a clear IMF rotation as one of its key signatures. So does an ordinary solar wind sector boundary crossing. The two phenomena are not identical. There are differences in the specific shape of the rotation, the accompanying density behavior, the ion composition, but those differences are the kind that require careful, multivariable analysis to establish, not the kind that jump out at you in a first pass of the data. Scientists studying this problem are aware that they may end up with a dataset that is genuinely ambiguous. Not incomplete, not wrong, but ambiguous in the sense that two equally valid interpretations of the same data, comet tail crossing versus solar wind fluctuation coinciding with CHHSS arrival, cannot be cleanly separated without additional constraints that the current instrument configuration may not provide. That ambiguity is not a failure of science, it is honest science. But it is also why the answer to the central question, did we detect PANSTARRS' tail, may remain genuinely uncertain for a long time. Part 8. The Observational Paradox. Let us map out the scenario space clearly, because it is worth understanding exactly what range of outcomes is possible before we move on to everything else happening simultaneously. In the best possible case, and this is genuinely best case, the April 24th through 26th, data shows a clean sequence, an IMF rotation of the right kind, at the right time, followed by a density change, followed by a compositional anomaly with the fingerprint of cometary heavy ions. Multiple spacecraft at different positions see consistent signals. The CHHSS arrives either just before or just after the tail crossing window, not simultaneous with it, giving a brief clean interval in the data. The solar wind is cooperative enough that the background can be modelled and subtracted with confidence. A team of scientists looks at all of this, compares it with orbital projections for PANSTARRS, and publishes a paper within a year saying, "We detected it." That would be extraordinary. It would represent only the second well-documented case in history of Earth's environment registering the passage of a comet's ion tail, the first being the Hyakutake case. And that was not detected in real time, it was found years later. A real-time or near-real-time confirmation would be a genuine advance in heliophysics. In the worst case, the CHHSS arrives precisely on schedule. KP climbs to 5 or above during the crossing window. The solar wind is turbulent and compositionally variable, and every dataset from that 48-hour period is dominated by the storm's signatures. The comet tail, if its signal is present at all, is completely buried. Scientists who look at the data later find it impossible to separate any potential comet signal from the CHHSS background. The result is a null detection, not a confirmed absence of a tail crossing, but an inability to confirm its presence. The crossing happened, probably. The data is too messy to say more. Between those extremes are the more probable middle outcomes. A dataset that contains some anomalies around the right time period, anomalies that are consistent with but not definitively attributable to a tail crossing. anomalies that will generate a small scientific debate for a year or two before the consensus settles or does not settle on an interpretation. This is the observational paradox at the centre of everything. The window is real, the geometry is real, the comet is real. But the act of observation itself is compromised by circumstances entirely beyond anyone's control, and there is something deeply philosophically interesting about that. About a universe that occasionally offers up these fleeting scientific opportunities, and then, through the sheer mechanical operation of other physical processes, makes those opportunities difficult to use. It is also worth acknowledging that science has been here before, not with comet tails specifically, but with the general problem of extracting signals from noisy, complex environments. Gravitational wave detection required building instruments so precise they could measure a displacement smaller than a proton, and then filtering out earthquake vibrations, passing trucks, thermal fluctuations, and 1,000 other noise sources. Exoplanet detection requires measuring stellar brightness changes of less than 1% and distinguishing them from the star's own variability. Heliophysics is not unique in facing this problem, it just faces it in a particularly frustrating way this week. The sun is making things harder. Earth is in the middle of its own dynamic environment, and something else entirely is about to add another layer of narrative confusion to an already complex situation. Something that has nothing to do with comets or solar wind, but that is going to collide with this story in the public consciousness in ways that are worth examining carefully. The Japan Trench is still moving. Part 9. The Japan Trench Timing Problem. On April 20th, a megathrust earthquake of magnitude 7.4 to 7.5 struck offshore Japan along the Japan Trench, one of the most seismically active subduction zones on the planet. The timing, relative to everything else we have been discussing, is notable. Not because the earthquake has anything to do with the comet or the solar activity, it does not. But because it happened first, before the coronal hole stream, before the peak of the PANSTARRS tail-crossing window, before all the other events converging on this week, and that temporal ordering matters enormously for understanding how and why these events will inevitably be linked in the popular narrative. Aftershock sequences following a major megathrust event follow a well-documented statistical pattern known as the Omori-Utsu law. The frequency of aftershocks decays over time in a specific predictable way. Many aftershocks immediately after the main shock, fewer as time goes on, but never zero for a long time afterward. A magnitude 7.4 event along the Japan Trench generates aftershocks that will continue for weeks, possibly months, with occasional larger ones, magnitude 4.5, 5.0, scattered throughout. The sequences tend to cluster spatially along the fault segment that ruptured, with some migration along adjacent sections. The ongoing aftershock sequence as Earth approaches the April 24th through 26th window is entirely consistent with this pattern. Multiple M4.5 and above events have been recorded since the main shock. They're occurring where the models say they should occur. They're occurring at the frequency the Omori-Utsu law predicts. There is nothing anomalous about them in seismological terms. The probability of a significant foreshock, technically, the probability of an aftershock in the 5.5 to 6.0 range, or larger before the sequence fully decays, is around 5 to 6% in any given week for a sequence of this size. That is not negligible, but it is also not elevated by any factor related to what is happening in space. The seismic hazard in this region is what it is, driven by the mechanical stress state of the subducting Pacific plate, and that stress state is not influenced by plasma tail geometry or solar wind speed. Here is where the detection problem we have been tracking, all video gets mirrored in an unexpected domain. Just as spacecraft data during the April 24th window will be difficult to interpret because multiple overlapping physical processes are producing similar-looking signals, the public narrative around this week's events faces a parallel problem. Multiple real events, an earthquake sequence, solar activity, a comet tail crossing, are converging in the same time window, and the human brain is spectacularly, almost pathologically bad at treating simultaneous events as coincidental. This is the timing problem. The earthquake happened on April 20th. The tail crossing window opens on April 24th. There is a 4-day gap between them, which is not nothing. The events are clearly separated in time, and causality moving backward is not a thing that happens in physics. But the aftershocks are ongoing. The sequence is still active during the window. From the outside, from a casual observer who sees earthquake sequence plus comet plasma plus solar storm all happening in the same week, the sequencing can blur, and the blurring is where false narratives germinate. The timeline is the immune system here. The earthquake preceded every other event in this story. It caused none of them. None of the other events caused it. Understanding that is not just academically important. It is the difference between reading this week's events as a series of independent coincidences or as some kind of connected phenomenon. They are the former. The data is clear on this, but clear data and compelling narrative have never been the same thing. Part 10. The narrative collision. The internet at this point in the story is already busy. If you have looked at social media or done any searching around the terms PANSTARRS or plasma tail or comet Earth in the past 48 hours, you have probably already encountered claims that range from the merely speculative to the genuinely unfounded. The most common one, and the one worth addressing directly because it sounds the most scientific on first pass, goes something like this. The incoming plasma from the comet's tail is electromagnetic in nature, and electromagnetic influences from space can affect Earth's geomagnetic field, and geomagnetic disturbances have been statistically correlated with increased seismic activity. Therefore, the comet is contributing to, or triggering the ongoing Japan Trench aftershocks. Each individual step in that chain contains some truth and some fiction in roughly equal measure, and the overall conclusion is not supported. Let us walk through it. The incoming plasma tail material is indeed electromagnetic in nature. Charged particles, magnetic fields, yes, accurate. The interaction of that material with Earth's environment, if detectable at all, would produce effects on the geomagnetic field. Also technically accurate, in the same sense that a moth landing on your car hood produces a measurable change in the car's momentum. True but irrelevant to any practical consequence. Geomagnetic disturbances have been studied for correlations with seismic activity for decades. The literature is extensive, contentious, and largely inconclusive. There are a handful of statistical papers claiming weak correlations under specific conditions, and a much larger body of work finding no significant relationship. None of the positive studies suggest a causal mechanism strong enough to be physically plausible given the energy scales involved. The timeline issue makes the claim structurally impossible before you even get to the physics. The earthquake happened on April 20th. The plasma tail interaction window starts April 24th. Causes do not follow effects. The comet's plasma did not travel backward in time to trigger a fault rupture 4 days before it arrived. If you encounter this claim, the timeline alone is sufficient to dismiss it. But there is a deeper issue worth addressing, which is why these narratives are compelling in the first place. The human brain is a pattern recognition machine. It evolved to find connections in noisy, complex environments, to look at apparently random events and ask, are these related? That tendency has served our species extremely well in many contexts. But it also generates false positives, systematically and predictably, whenever multiple unusual or dramatic events occur in close temporal proximity. We are wired to see the alignment, to feel the significance of convergence, and to resist the explanation that it is all coincidence. The convergence this week is real. 5 distinct unusual events in 48 hours, we will enumerate them properly in Act 4, is genuinely rare in a statistical sense. But rare does not mean connected, and the fact that something feels significant is not evidence that it is. This is perhaps the most important epistemological lesson this week can teach, and it applies equally to the scientific problem of detecting the comet's tail. Just as we must be careful not to mistake a solar wind fluctuation for a comet signature, we must be careful not to mistake temporal coincidence for causal connection. The discipline is the same. Separate the signal from the story you want to tell about it. Part 11. The energy budget that kills the theory. The most efficient way to evaluate any claim about space weather causing earthquakes is to ask a simple question. Do the numbers work? Not philosophically. Not in terms of statistical correlations, just in terms of raw energy. Does the amount of energy involved in the space weather event come anywhere close to the amount of energy required to trigger or modify a seismic rupture? A magnitude 7.4 megathrust earthquake releases on the order of 10 to the 15th joules of seismic energy. That is approximately equivalent to tens of thousands of nuclear weapons detonated simultaneously. That energy comes from the slow build-up of elastic stress in tectonic plates over hundreds or thousands of years, a mechanical spring essentially, compressed over geological timescales and released in seconds. The electromagnetic energy delivered to Earth's environment by the passage through a comet's ion tail, even assuming the most optimistic estimates of tail density at Earth's position, is orders of magnitude smaller. We are comparing something in the range of 10 to the 15th joules to something that is perhaps 12 to 15 orders of magnitude less energetic. The comet's electromagnetic footprint at Earth, if detectable at all by sensitive spacecraft instruments, is essentially imperceptible as a mechanical force on Earth's solid crust. Even the most energetic space weather events, major geomagnetic storms driven by large coronal mass ejections, events that cause widespread power grid disruptions and satellite failures, do not deliver enough energy to the solid Earth to meaningfully alter the stress state of a locked fault. The coupling between the electromagnetic effects in the ionosphere and magnetosphere and the mechanical behaviour of the lithosphere is extraordinarily weak. The Earth's crust does not respond to magnetic field changes the way a compass needle does. It responds to stress and strain, and the stresses involved in megathrust seismicity are geological in scale, measured in megapascals maintained over centuries. The solar seismic correlation literature, to the extent it claims any relationship, is dealing with effects that are so small as to be barely distinguishable from statistical noise, and the proposed mechanisms, changes in atmospheric pressure, modulation of ionospheric electrical currents, piezoelectric effects in the crust, all operate at energy scales far below what would be needed to trigger a significant earthquake. At best, some researchers have suggested that space weather effects might slightly modulate the timing of ruptures that are already critically stressed and about to occur anyway, the way a single additional grain of sand might determine when an already unstable pile collapses. At worst, the correlations are artifacts of the analysis methodology, disappearing when more robust statistical techniques are applied. The bottom line for the PANSTARRS Japan trench connection specifically, the energy is wrong by more than 10 orders of magnitude. The timeline is wrong by 4 days. The causal direction is wrong. There is no mechanism. The claim does not survive contact with physics. But the fact that we have to make this argument at all, the fact that the claim will circulate and be believed by a meaningful fraction of people who encounter it, is itself a signal worth detecting, one that connects directly back to the core question of this video. Distinguishing real signals from noise is hard. It is hard in spacecraft data, and it is hard in public discourse, for related but distinct reasons. The tools are different, peer review versus media literacy, but the underlying challenge is the same. Part 12. The real risk, not what people think. If you want to identify the actual documented, operationally significant risk associated with the space weather conditions of the April 24th through 26th window, you need to stop looking at the ground and start looking at orbit. The elevated electron flux that has been running for multiple days in a row represents a real hazard to spacecraft. Not a catastrophic one, not the kind that makes headlines, but the kind that operations teams monitor carefully, and that, on statistical timescales, contributes to the degradation and eventual failure of satellite systems. The mechanism is called deep dielectric charging, and it works like this. High-energy electrons, the kind that are elevated right now, can penetrate the outer surfaces of spacecraft and accumulate inside the dielectric materials of the satellite's electronics. As the charge builds up, it can eventually discharge suddenly and internally, producing a pulse of current that damages or destroys electronic components. It is like a miniature lightning strike inside the satellite's own circuit boards, happening without warning. The risk is not uniform across all satellites. Lower Earth orbit spacecraft, protected by the magnetic field topology, are less exposed than those in medium Earth orbit or geosynchronous orbit. GPS satellites, communications satellites, weather monitoring platforms, these are more exposed. Operations teams during elevated electron flux periods typically implement precautions, reducing radiation-sensitive activities, monitoring charge accumulation indicators, having contingency procedures ready. There is also the standard array of concerns during periods of elevated geomagnetic activity. Increased atmospheric drag on low-orbit satellites, requiring orbit maintenance burns. Increased ionospheric variability, degrading GPS accuracy. High-frequency radio communication disruptions affecting aviation and maritime operations. These are not exotic or catastrophic effects, but they are real, documented, economically significant impacts of space weather on human infrastructure. Here is the attribution problem that connects this directly back to the central thread. If a satellite experiences an anomaly during the April 24th through 26th window, and statistically, given the elevated space weather conditions, the probability of some satellite anomaly during this period is non-negligible. What caused it? Was it the coronal hole stream, the active region activity, the elevated electron flux? Or could some fraction of it be attributed to the passage through the comet's plasma tail? From the operations perspective, the answer almost certainly will not distinguish between these possibilities. The satellite failed, or degraded, or required a safing procedure, and it happened during elevated space weather. The comet gets no credit and no blame. But in the public narrative, especially if someone is already primed to connect the comet to every event of the week, any satellite anomaly becomes potential evidence for the plasma tail's effects. This is the mirror image of the scientific detection problem. Scientists are trying to find a genuine signal in noisy data by carefully removing all the other known sources. The public narrative runs the opposite process. It takes any anomalous event and attributes it to the most dramatic available cause without doing the careful subtraction work. The result is a kind of perpetual motion machine of confirmation bias, where every event reinforces the narrative regardless of what the actual cause was. The real risk this week is precisely that. Not earthquakes triggered by plasma. Not catastrophic satellite failures caused by a comet's tail. The real risk is the ongoing, culturally pervasive conflation of coincidence with causation, a cognitive tendency that no coronal hole can excuse, but that no amount of careful scientific communication seems to fully cure. Part 13. The Lyrid interference layer. While all of this is unfolding in the invisible plasma environment of interplanetary space, there is something else happening that is visible, beautifully, accessibly visible, and that is pulling public attention toward the sky in ways that add a final layer of observational confusion to the week. The Lyrid meteor shower is peaking. The Lyrids arrive every April when Earth crosses the debris trail left by Comet C/1861 G1, otherwise known as Comet Thatcher, a completely different comet with no relationship whatsoever to PANSTARRS. Comet Thatcher has not been seen since 1861, and its debris trail is well charted, predictable, and entirely separate from everything else being discussed here. The Lyrids produce around 10 to 20 meteors per hour at peak under good conditions, with occasional outburst years producing more. The irony of the Lyrids' timing is almost theatrical. Earth is simultaneously crossing through the debris trail of one comet and possibly through the plasma tail of another, and the former is spectacular and visible, while the latter is completely invisible and would require sensitive spacecraft instruments and months of analysis to confirm. One event lights up the sky. The other might leave a 1 part per million trace in a dataset that fewer than 100 scientists will ever examine. This visible versus invisible contrast is the point. What connects back to the central thread here is the way the Lyrids will draw attention to comet-related phenomena this week, in a way that is real, but fundamentally misleading about where the actual scientific interest lies. Videos and posts about the Lyrid meteor shower this week will inevitably bleed into discussions of PANSTARRS and the plasma tail, conflating visible, harmless meteor activity with the entirely different and scientifically distinct question of plasma tail detection. The Lyrids are beautiful, they are interesting in their own right, but they are a distraction from the subtle, invisible, instrumentally demanding event that is actually the scientifically novel thing happening this week. Part 14. The Moon's Quiet Influence. There is one more celestial calendar entry for this week that will appear in lists of converging events. On April 24th, the Moon is at first quarter phase. The Moon's gravitational influence on Earth is real and significant. It drives the tides, both oceanic and, to a much smaller degree, solid Earth tides, which are genuine deformations of the planet's crust caused by the tidal gravitational gradient. Researchers have examined whether tidal loading, the change in crustal stress caused by these solid Earth tides, can influence earthquake occurrence. The statistical literature here is slightly more credible than the space weather seismic connection literature, in the sense that a weak statistical preference for certain types of earthquakes, near tidal stress maxima, has been reported in some fault systems. But weak statistical preference is very different from the Moon causes earthquakes, and the effect size, where it exists at all, is tiny relative to the tectonic driving forces. First quarter phase is also, seismologically speaking, not a particularly special configuration. The extremes of tidal loading correspond to full moon and new moon, the syzygy configurations where the sun and moon are aligned and their gravitational effects add together. First quarter is the intermediate configuration, a quadrature, where the sun and moon are at 90 degrees from Earth's perspective. Tidal forces at quadrature are actually near their minimum for the month, not their maximum. If you were going to argue for a tidal seismic trigger this week, the lunar phase would actually be one of the weaker possible choices for that argument. The moon's presence in the convergence event list this week is more an artifact of calendar coincidence than physical significance. It connects back to the main story only in this way: the instinct to include it. To see the lunar phase as one more sign that something meaningful is happening is the same instinct that mistakes solar wind fluctuations for comet signatures. Pattern recognition, running ahead of evidence. It is natural, it is human, and it is exactly the cognitive habit that both scientists and informed observers need to consciously resist this week. Part 15, the alignment illusion. So let us name all 5 events. Let us put them on the table together and look at them clearly, because the convergence is real, the rarity is real, and it deserves to be examined seriously rather than either hyped or dismissed. Event 1, Comet PANSTARRS making perihelion passage inside Mercury's orbit, with Earth geometrically positioned to cross its projected ion tail during April 24th through 26th, a genuinely rare orbital configuration. Event 2, active region 4420 with beta-gamma magnetic complexity, present on the Sun's Earth-facing disk, producing ongoing flare activity and introducing variability into the interplanetary magnetic field. Event 3, a coronal hole high-speed stream forecast to arrive at Earth on approximately April 24th, bringing solar wind speeds of 600 to 700 km per second, and expected geomagnetic activity of kp 4 to 5. Event 4, the ongoing Japan Trench aftershock sequence following the April 20th magnitude 7.4 to 7.5 megathrust earthquake. Event 5, the Lyrid meteor shower at peak with Earth crossing Comet Thatcher's debris trail, and the first quarter moon on April 24th. Now let us look at these 5 events honestly. Each one is, on its own, an event that might generate a science news headline on a slow week. Any one of them in isolation would be interesting. Together in the same 48 hours, they feel extraordinary. They feel like something. The question is whether that feeling corresponds to anything real. The honest answer from physics is no, not in the way the feeling suggests. These events are driven by completely independent physical systems. The comet is on an orbital trajectory determined by its formation billions of years ago and subsequent gravitational perturbations. The sunspot region formed from magnetic flux emerging through the solar surface, following a pattern of solar cycle activity that has nothing to do with cometary geometry. The coronal hole high-speed stream is a consequence of the Sun's rotating magnetic topology. It was produced before anyone noticed the comet's alignment. The Japan Trench earthquake was driven by the subduction of the Pacific Plate, which has been operating on timescales of tens of millions of years. The Lyrids follow a calendar determined by Comet Thatcher's entirely separate orbital debris trail. Not one of these systems knows the others exist. Not one of them is influenced by the others in any meaningful physical way. They are coincident in time the way a bus, a bird, and a falling leaf might all pass your window in the same minute. Not because they are connected, but because you were watching. Human pattern recognition, however, sees something else. It sees the 5 events and constructs a narrative around their simultaneity. It imputes significance to the convergence. It asks, why now? As if now were a special coordinate in the universe's causal structure, rather than simply the present moment, which would inevitably contain whatever events happen to be active at the time. Every week is now to someone. But most weeks do not have 5 headline-generating events overlapping, so most weeks do not trigger the narrative reflex. The statistical rarity of this specific combination of events, 5 events of roughly this magnitude in the same 48-hour window, has been estimated at around 0.1 to 0.5%, depending on how you define the categories and count the base rates. That is rare in the everyday sense of the word. But across the history of the solar system, across the billions of years Earth has been orbiting the Sun, This specific configuration, or something very like it, has occurred many times. We are not special for experiencing it. We are just the observers present at this particular instance of it. The deeper point, which connects directly back to the central question of whether PANSTARRS' tail will be detected. The rarity of the convergence is actually partly responsible for the scientific opportunity. The fact that a comet is near perihelion, that it has an active ion tail, that Earth happens to be geometrically positioned to cross its projection, that specific alignment is rare precisely because it requires multiple independent orbital and physical factors to coincide. The rarity is real. The significance of the convergence as a unified meaningful event is not. What is worth holding on to from this convergence is the observational opportunity it creates. Multiple unusual conditions active simultaneously mean multiple unusual datasets being collected. Scientists studying solar cometary interactions, geomagnetic variability, and seismic behavior all have interesting data from this window. The interpretation of each piece of data will proceed independently, using the methods appropriate to each field, and the results will be published in separate papers aimed at separate scientific communities. None of those papers will argue that the events were connected, but collectively they may produce an unusually rich picture of what a particularly active week looks like across multiple physical systems simultaneously. That is what alignment means to a scientist, not a sign, a data set. Part 16, the probability trap. There is a specific cognitive trap that this week's convergence exemplifies, and it is worth naming directly, because it has real practical implications for how you interpret not just this story, but the next 6 months of online content about everything we have discussed here. The trap works like this. You observe 5 rare events landing in the same 48-hour window, and you do what any reasonable person does. You try to estimate the odds. You figure each event occurs with some frequency. Let us say, for illustrative purposes, that each of the 5 events is roughly a once-per-month occurrence. That is actually broadly consistent with the real frequencies involved here. A magnetically complex active region on the Sun facing Earth, maybe once or twice a month. A coronal hole high-speed stream arriving at Earth, several times a month but not constant. A significant earthquake sequence in a major subduction zone, uncommon but not rare across the whole planet. A comet at perihelion inside Mercury's orbit with a tail geometry crossing Earth's path, genuinely rare, though not impossible to estimate a base rate for. A meteor shower peak, predictable, calendar regular. Now you assume independence, which is physically accurate as we have established, because none of these systems talk to each other, and you multiply the probabilities together. 5 once-per-month events in the same 48 hours out of roughly 730 hours in a month. Run that calculation and you get something in the neighbourhood of 1 in 25 million, maybe lower. The exact number depends on your assumptions, but the point is it sounds extraordinary. It sounds like the kind of number that cannot be a coincidence. It sounds frankly like it means something. But here is the problem. That calculation contains a fatal error. And the error is so common, so seductive, and so consistently overlooked that it has its own name in statistics. It is called the look elsewhere effect. Sometimes it gets called the multiple comparisons problem. Either way, it refers to the same fundamental mistake, and once you see it, you will start noticing it everywhere. The calculation correctly computes the probability of these specific 5 events occurring together in this specific window. That part is fine. The error is that it completely fails to account for why you are doing this calculation in the first place. You are calculating the probability of this convergence because you noticed it, because something unusual appeared to be happening and you wanted to quantify how unusual it was. And that act of noticing, of selecting this particular window for analysis because it seemed remarkable, introduces a bias that blows the probability estimate by an enormous factor. Think about what you are really asking. You're not asking, what is the probability that this specific combination of events occurs in this specific window? You're actually asking something closer to, given that I am scanning a continuous timeline of events, and I will stop and calculate whenever something looks unusual, how often will I find windows that look like this? And the answer to that second question is regularly. Constantly, almost. Because there are always multiple events occurring simultaneously across the solar system, across Earth's tectonic plates, across the astronomical calendar. The human brain is extraordinarily good, almost embarrassingly good, at finding subsets of those events that can be framed as a meaningful convergence. We are pattern recognition machines. We were built for this. And in most evolutionary contexts, this was a fantastic feature. Spotting the connection between two events that actually were related, the rustling in the grass and the predator, was survival. The cost of a false positive was low, the cost of missing a real connection was high, so we evolved to err heavily on the side of finding patterns. Here is a thought experiment that makes the problem concrete. Pick any 48-hour window in the past 10 years, any window at all. Now go back and identify the 5 most unusual space weather, seismic and astronomical events that happen to overlap with it. You will find something almost every single time, because there are always active regions on the sun, always aftershock sequences somewhere on the planet, always meteor showers somewhere in the calendar, always solar wind disturbances of one kind or another. The question is never whether you can find a convergence. The question is whether the convergence you found means anything beyond the fact that you were looking for it. This is not abstract philosophy. And here is why it matters directly for the story we're telling in this video. The same principle that makes 5 events in 48 hours seem impossibly significant is the exact same principle that makes false positives in scientific data seem compelling. When a scientist sits down with a dataset from April 24th through 26th and starts looking for a comet tail signature, they are subject to exactly this cognitive pressure. The brain wants to find the pattern. The brain is good at finding patterns. And if the analyst is not extremely careful, if they do not apply the right methodological safeguards before they even open the data, they will find something that looks like a comet signature whether one is there or not. Not because they are dishonest, not because they are incompetent, but because the human visual and analytical system, left to its own devices, will generate apparent signals out of noise with remarkable efficiency. This is why the rigorous scientific response to problems like this involves steps that can look, from the outside, almost absurdly conservative. Pre-registering hypotheses before looking at the data means writing down exactly what you're going to look for and what will count as a detection before you ever open the dataset. That way, you cannot unconsciously adjust your definition of signal after you have already seen what the data looks like. Applying corrections for multiple comparisons means accounting mathematically for the fact that if you test 20 possible hypotheses in one dataset, you should expect roughly one of them to appear statistically significant by chance alone, even if none of them are real. Requiring blind analysis means having the statistical test performed by someone who does not know which time periods correspond to which physical events, so the analysis cannot be unconsciously steered toward a preferred outcome. Demanding independent replication means the result only becomes credible when a completely separate team, with completely separate data from a completely separate instrument, finds the same thing. These requirements are not bureaucratic box ticking. They are not the scientific community being unnecessarily cautious or slow or conservative for the sake of it. They are the immune system of scientific inference. They are the specific set of tools that evolution did not give us, because evolution had no reason to make us good at distinguishing rare real signals from compelling-looking noise in heliophysics datasets, and that we had to build from scratch through a few centuries of painful experience with how badly things go wrong when you skip them. The scientists who will eventually analyze the April 24th through 26th spacecraft data will apply exactly these methods. They will not open the dataset, spot something interesting near the predicted crossing time, and immediately write a press release. They will establish their detection criteria before they look. They will define in advance what combination of magnetic field signature, density anomaly, and ion composition change will constitute a confirmed detection versus an ambiguous result versus a non-detection. They will quantify the expected false positive rate given the background conditions, the coronal hole stream, the active region activity, all of it. They will require consistency across multiple spacecraft at multiple positions. They will submit to peer review, where other scientists who are not involved in the analysis will scrutinize every methodological choice and push back on anything that looks like motivated reasoning. It is slow. It is unglamorous. It produces results on timescales of months to years rather than hours to days, and it is exactly what the data demands, because the data does not care about our narrative preferences. The data does not care that we have 47 hours on the clock and a story that feels like it wants a dramatic ending. The data is just numbers, and the numbers will say what they say, and the only way to know what they are actually saying, rather than what we want them to say, is to apply the immune system rigorously and let it do its job. Whether that rigour gets rewarded with an actual detection or confirms a null result depends entirely on physics. Not on the convergence, not on how remarkable the timing feels, not on how many events are clustering in the same window, on physics. And speaking of physics, we need to talk about exactly where that physics plays out. Because right now, at this moment, there are spacecraft sitting 1.5 million kilometres from Earth, collecting the data that will eventually answer every question we have been building toward. And what those spacecraft are, what they measure, and why their geometry matters as much as anything else in this story is where we are going next. Part 17. Where the evidence will come from. 1.5 million kilometres from Earth, in the gravitational balance point where the Sun's pull and Earth's pull exactly cancel each other out, sits a small fleet of spacecraft that most people have never heard of. They have no crew, they produce no dramatic imagery, they do not trend on social media, but they are the reason we have any hope at all of detecting something as faint as a comet's ion tail in the roiling, turbulent plasma environment of the inner solar system. This is the first Lagrange point, L1, and what is stationed there right now is the closest thing humanity has to an early warning system for everything the Sun decides to throw at us. To understand why L1 matters, you need to picture the geometry. Earth is moving through space at roughly 30 kilometers per second, orbiting the Sun in a path that takes 1 year to complete. The Sun is constantly exhaling, sending a continuous stream of charged particles outward in all directions, the solar wind, travelling at hundreds of kilometers per second. Anything that is going to hit Earth in the form of a solar wind disturbance, a coronal hole stream, a coronal mass ejection, a density enhancement, or theoretically a comet's plasma tail, has to pass through the L1 point roughly 45 minutes to an hour before it reaches Earth itself. That 45-minute lead time is not much, but it is enough to trigger alerts, warn satellite operators, prepare power grid managers, and, for our purposes, record the arriving plasma environment in detail before it gets complicated by Earth's own magnetosphere. The three spacecraft that matter most for the PANSTARRS detection question are ACE, DSCOVA, and Stereo A. Each one brings something different to the problem. Together, they form something more powerful than any individual instrument could manage alone. Start with ACE, the Advanced Composition Explorer. It has been operating since 1997, which makes it a genuine veteran of the L1 fleet, nearly 3 decades of continuous solar wind monitoring from the same gravitational perch. For most space weather purposes, ACE is respected but not glamorous. It measures things, it archives things. It has been doing this reliably for so long that its data record is one of the most valuable continuous data sets in heliophysics, not because any single measurement is extraordinary, but because the sheer length of the record gives you context that newer instruments simply cannot provide. When something unusual shows up in a CE data, you can compare it against 27 years of baseline measurements and ask whether this is genuinely anomalous or just within the normal range of solar wind variability. That historical context is irreplaceable. But ACE's specific superpower for the PANSTARRS problem is its ion composition capability. The Solar Wind Ion Composition Spectrometer, SWICS, can measure the charge state distribution and elemental abundance of ions in the solar wind with a precision that is genuinely unmatched among operational L1 instruments. This matters because the most chemically diagnostic signature of a comet tail crossing is not a magnetic field rotation or a density change. Both of those can be produced by ordinary solar wind structures. The most diagnostic signature is a compositional anomaly, specifically the presence of ions that have charge states inconsistent with formation in the solar corona. Cometary ions are produced by photoionization of outgassed molecules at relatively low temperatures near the comet's nucleus. They carry different charge fingerprints than ions that were stripped of their electrons in the multi-million degree solar corona. If PANSTARRS' tail leaves any chemical trace in the arriving plasma during the April 24th through 26th window, ACE has the best chance of any instrument currently operating of seeing it. The catch, and there is always a catch this week, is that the coronal hole high-speed stream arriving at essentially the same time also changes the ion composition of the solar wind in characteristic ways. Fast wind from coronal holes has a different elemental fractionation pattern than slow wind, different oxygen charge state ratios, different ion abundances. These changes are well documented and can in principle be modelled and subtracted from the dataset. But subtracting a large, well-understood signal to find a small, uncertain one underneath it is exactly the kind of analysis that takes months to do carefully. Nobody's going to look at ACE data on April 26th and immediately say they found a comet. The composition analysis alone will take weeks at minimum. DSCOVR, the Deep Space Climate Observatory, is a different kind of instrument with a different kind of role. Where ACE is a scientific research platform optimized for detailed composition measurements, DSCOVR is an operational monitoring system. It is the primary real-time data feed for NOAA's Space Weather Prediction Center. Its magnetometer and plasma sensors are providing continuous measurements of solar wind speed, density, temperature, and magnetic field direction, and that data is being transmitted to ground stations and processed into public feeds with a latency of only a few minutes. If you have ever looked at a space weather website and seen real-time solar wind data, you are almost certainly looking at DSCOVR data. It is the heartbeat monitor of the L1 fleet, not the most scientifically sophisticated instrument, but the most operationally critical and the most immediately accessible. For the PANSTARRS detection question, DSCVR's magnetic field data is particularly relevant. An interplanetary magnetic field rotation of the kind associated with a comet tail crossing, the hairpin-shaped signature produced by magnetic draping around the cometary obstacle, would show up in DSCOVR's magnetometer data relatively clearly if it were large enough. Whether it will be large enough at Earth's distance from PANSTARRS' nucleus, and whether it will be distinguishable from the magnetic field rotations that the coronal hole stream will independently produce, is exactly the uncertainty we keep returning to. DSCOVR will see the coronal hole stream loudly and clearly. Whether it will see the comet underneath the stream is the question nobody can answer in advance. And then there is Stereo A. This is the one that makes the detection problem genuinely three-dimensional, and it is the spacecraft whose role in this specific story is most underappreciated. Stereo, Solar Terrestrial Relations Observatory, was originally launched as a pair of spacecraft designed to provide the first stereoscopic imaging of the sun and the solar wind. The idea was straightforward. Put one spacecraft ahead of Earth in its orbit and one behind, separated by increasing angles over time, and use the two vantage points together to build three-dimensional models of solar wind structures the way two eyes build a three-dimensional view of the world. Stereo B was lost in 2014 after a communications failure. Stereo A is still operating, currently positioned ahead of Earth in its orbital motion by some tens of degrees, in heliocentric longitude, not at L1, but at roughly the same distance from the Sun, displaced laterally in a way that gives it a fundamentally different view of the same interplanetary environment. That lateral displacement is what makes Stereo A so valuable for this event. A comet's ion tail is not a flat plane. It is a three-dimensional structure with width, depth, and density gradients that vary across its cross-section. Earth, sweeping through its orbital motion, will intersect some particular cross-section of that tail at some particular time during the window. Stereo A, approaching the same tail region from a different angle and at a different time, will intersect a different cross-section. If both spacecraft record anomalies that are consistent with what the tail's three-dimensional geometry would predict for their respective positions, that multi-point correlation is enormously more convincing than anything a single spacecraft could provide. This is the decorrelation test, and it is one of the most powerful analytical tools available for separating a real physical signal from noise. Here is the core logic. Solar wind fluctuations, the kind produced by coronal hole streams, active region outflows, and ordinary solar wind turbulence, are not perfectly correlated between two spacecraft separated by tens of millions of kilometers. They can be partially correlated if they originate from the same solar source region, but the correlation weakens with separation distance and time delay. A coherent structure like a comet's tail, on the other hand, should produce anomalies at both spacecraft in a way that is predictable from the tail's geometry. You can calculate, based on the orbital mechanics and the tail's projected orientation, when each spacecraft should cross the tail and what the signal should look like at each position. If the data matches those predictions at both spacecraft, the case for a real detection becomes very strong. If only one spacecraft sees anything, or if both see anomalies that do not fit the geometric predictions, the case collapses. The data from all three spacecraft is flowing right now. Some of it is publicly accessible through space weather data portals within minutes of acquisition. You could go look at it yourself if you know where to find it and what you're looking at. The instruments are working, the window is open, the geometry is in place. The challenge has never been getting the data. The challenge is knowing what to look for, having the models sophisticated enough to interpret what you see, and doing all of this while a coronal hole high-speed stream is producing signals in the same dataset that are orders of magnitude larger than anything the comet might leave behind. The data will have answers in it. Whether anyone can hear those answers through the noise the sun is generating right now is what the next few months of analysis will determine. And what specifically are scientists looking for in that data? The exact signatures in the exact sequence that would constitute a credible detection. That is what we need to go through next. Part 18. What scientists are actually looking for. Picture a heliophysicist sitting at a terminal on April 24th. Multiple data streams are open on the screen simultaneously. Solar wind speed, magnetic field direction, proton density, ion composition ratios. The numbers are updating every few minutes, sometimes faster. Somewhere inside that river of numbers, there may be a signal from a comet that has not visited the inner solar system in thousands of years. Or there may not be. The only way to find out is to know exactly what you're looking for, and to know, with equal precision, what you're not looking for, because this week the data is going to be full of things that almost look right but are not. So let us go through it. What does a comet tail crossing actually look like in spacecraft data? What are the specific signatures in what sequence that would constitute a credible detection? And why is each one individually insufficient, requiring all of them together before anyone can responsibly make a claim? The first and most immediately visible indicator is an interplanetary magnetic field rotation with a very specific profile. Not just any rotation, the IMF changes direction all the time, constantly, as different solar wind structures sweep past the L1 monitors. What makes a comet tail rotation distinctive is its shape, the geometry of how it happens, and to understand that you need to understand what magnetic draping actually is. When a comet is actively outgassing, which PANSTARRS absolutely is right now, burning through perihelion inside Mercury's orbit, it is releasing enormous quantities of neutral molecules into the surrounding space. Those molecules get ionized almost immediately by solar radiation, turning into charged particles that interact with the solar wind and the interplanetary magnetic field. The solar wind cannot simply flow through this ionized material the way it flows through empty space. It has to flow around it, the way a river flows around a boulder sitting in the current. And as it flows around, it drags the magnetic field lines with it, stretching them, bending them, wrapping them around the cometary obstacle and then pulling them out behind the nucleus into the tail. The result is a magnetic structure that looks, if you could see it in cross-section, like a folded hairpin. Two lobes of magnetic field draped around the nucleus and extending backward into the tail, with the field direction in one lobe pointing roughly toward the sun, and the field direction in the other lobe pointing roughly away from the sun, separated by a thin current sheet running down the center of the tail. When a spacecraft crosses through this structure from one side to the other, the magnetic field vector does not just flip randomly. It rotates through a specific sequence, increasing gradually in magnitude as the spacecraft approaches the tail boundary, then making a sharp directional change as it crosses the central current sheet, then reversing the sequence symmetrically as it exits the other side. That specific shape, the gradual approach, the sharp central rotation, the symmetric exit, is the magnetic fingerprint of a tail crossing. It is what Ulysses recorded at Hyakutake, buried in 1996, data that nobody recognized until the year 2000. It is the theoretical target that the Dieskova magnetometer and the ACE magnetic field instrument will be scanning for during the April 24th through 26th window. The challenge is that this shape, while distinctive in a clean dataset, can be partially mimicked by other solar wind structures, sector boundary crossings, CIR boundaries, and various kinds of magnetic discontinuities that the solar wind produces on its own. The coronal hole stream arriving during the window will produce its own magnetic field rotations, its own boundary crossings, its own sharp directional changes. Distinguishing a comet tail rotation from a coronal hole boundary rotation requires looking at the accompanying context, the density, the composition, the geometry, which is exactly why no single indicator is sufficient on its own. The second indicator is a proton density decrease inside the tail. This one is more intuitive once you understand the basic physics. The cometary plasma, the ionized gas streaming off the nucleus, is not dense enough to add significantly to the total particle count at Earth's distance. What it does instead is partially displace the ambient solar wind. The region inside the tail contains some cometary material and somewhat less solar wind material than the surrounding space. The net effect is a measurable decrease in proton density as a spacecraft enters the tail region. Not dramatic, not the kind of thing that shows up as a sharp cliff in the data, more like a valley, a gradual decrease as the spacecraft approaches the tail center, a minimum at or near the center, and a recovery on the other side. The size of that density decrease depends on the tail's cross-sectional density profile at Earth's distance from the nucleus, which is genuinely unknown in advance. Models can estimate it, but the uncertainty range is large. The most optimistic scenario, a coherent, relatively dense tail cross-section, might produce a density decrease of 10 to 30% relative to the surrounding solar wind. The Ulysses crossing at Hyakutake showed roughly a factor of 2 decrease, which is on the larger end of what current models would predict for PANSTARRS at Earth's distance. A 10% decrease is detectable in principle, but it requires a stable, well-characterized baseline to measure against. During a coronal hole high-speed stream passage, the proton density is already varying by 20 to 40% on timescales of hours just from the normal structure of the stream. Pulling a 10% comet signal out of that background is exactly the kind of problem that requires months of careful analysis rather than a quick glance at a real-time plot. The third indicator, and this is the one that gets scientists most excited because it is the hardest to fake, is the heavy ion composition anomaly. This is where the chemistry of the comet becomes a fingerprint that is genuinely difficult for the solar wind to replicate on its own. Here is the key. The solar wind carries heavy ions, oxygen, carbon, silicon, iron, but those ions were produced in the solar corona, a plasma with temperatures of 1 to 3 million degrees. At those temperatures, electrons are stripped from atoms very efficiently, leaving ions with high charge states. Solar wind oxygen is predominantly O6+ and O7+. Solar wind carbon is predominantly C5+ and C6+. These high charge states are the signature of coronal origin. They reflect the extreme temperature of the environment where the ions were formed. Cometary ions are produced in a completely different environment. When solar radiation ionizes the molecules outgassing from a comet's nucleus, water, carbon monoxide, carbon dioxide, and various other volatile compounds, it does so at much lower effective temperatures, near the comet's surface, far from any million-degree plasma. The resulting ions carry low-charge states. Cometary oxygen tends to appear as O+ or O2+. Cometary carbon comes primarily from molecules like CO+, carbon monoxide that has lost a single electron, rather than from the highly stripped carbon ions you find in the solar wind. This difference in charge state distribution is what ACE's solar wind ion composition spectrometer was built to detect. It is not looking for more oxygen in the generic sense. The solar wind already has oxygen, and the coronal hole stream will bring its own oxygen with its own characteristic fractionation pattern. It is looking for oxygen and carbon with the wrong charge states for the solar wind. Specifically, it is looking for low-charge state heavy ions that could only have been produced near a cold surface, rather than in a hot corona. And then there is CO+, ionized carbon monoxide. This molecular ion is not produced in any significant quantity by solar processes. The corona does not outgas carbon monoxide. If ACE detects CO+ above its background threshold during the April 24th through 26th window, that detection is close to definitive evidence of cometary material. It is the chemical smoking gun. The question, always the same question this week, is whether the concentration of CO+ in PANSTARRS' tail at Earth's distance is large enough to clear the instrument's detection threshold given the noise environment it is operating in. Beyond these three primary indicators, there is a broader analytical approach called statistical stacking that becomes relevant when no single measurement is individually compelling. Rather than demanding one perfect textbook clean signal from one instrument at one time, Statistical stacking looks for consistent patterns across multiple instruments, multiple time periods, and the full three-dimensional geometry of the crossing prediction. If the orbital models predict the crossing center at a specific time, and if that specific time shows up as an anomaly time in the magnetic data, and the density data, and the composition data simultaneously, even if each individual anomaly is marginal, the combined statistical weight can be significant. It is the scientific equivalent of triangulation. No single line of evidence points definitively to the answer, but multiple lines of evidence all pointing to the same location in time and space is harder to dismiss than any one of them alone. Whether the data will cooperate with any of this, whether the signals will be there at all, and whether they will be distinguishable from everything else happening in the same window is something no amount of analysis can answer in advance. The physics either left a mark or it did not, and the most likely outcome of the next few months of work is not a clean yes or no. It is something more honest, more uncertain, and in its own way more interesting than either of those. Part 19, the most likely outcome. Let us be honest about probability. Not the kind of probability that sounds impressive in a headline, not the 1 in 25 million convergence number we dismantled earlier, but the straightforward, unsentimental assessment of what is most likely to actually happen when scientists sit down with the April 24th through 26th data set and start looking for a comet that may or may not have left a mark. Given everything we have covered, the tail's expected diffuseness at Earth's distance from the nucleus, the elevated solar wind background that was already running hot before the window even opened, the coronal hole high-speed stream arriving at essentially the worst possible moment, the magnetic complexity being introduced by AR 4420 on the Sun's Earth-facing disk, and the fundamental detection threshold challenges that would exist even under ideal conditions, what does the probability landscape actually look like? What are the realistic outcomes, ranked honestly by likelihood, with no narrative preference attached? The most likely outcome is this. Earth does cross through some region geometrically associated with PANSTARRS' ion tail. The crossing is real in the physical sense. The planet moves through space that contains, or recently contained, material that originated from the comet's nucleus. But the spacecraft data from that window produces no clearly identifiable signal during or immediately after the event. Not because nothing happened, not because the tail was not there, but because the signal-to-noise ratio, under the actual conditions that prevailed, is insufficient for confident identification. The crossing happens, the instruments record it, in the same way they record everything, faithfully, without judgment, without knowing what they are supposed to be looking for. And the cometary signature, if present at all in the numbers, sits below the threshold where anyone can confidently separate it from everything else going on simultaneously. This outcome is not a failure. It is important to say that directly because the language of detection and non-detection can make it sound like something went wrong. Nothing went wrong. The geometry was correct. The instruments were working. The scientists were watching. But nature does not owe us a clean signal, and the conditions this week are genuinely unfavourable for extracting a subtle one. The ambiguity that results from this outcome is itself informative. It tells you something about the density of PANSTARRS' tail at Earth's distance, about the coherence of its structure across half an astronomical unit, about the practical limits of what current instruments can resolve against this particular background. A non-detection with known noise conditions is a constraint. It is data. It is not nothing. The second most likely outcome is what scientists would formally describe as a null result, and there is an important distinction between a null result and the ambiguous outcome just described. In the ambiguous scenario, the data contains interesting features that cannot be definitively attributed to the comet, but cannot be definitively ruled out either. In a genuine null result, the coronal hole stream and the active region produce such dominant signatures during the window that post-event analysis finds nothing above background that could plausibly be attributed to cometary material even with generous assumptions. The tail crossing remains geometrically consistent with having occurred, but the data offers no positive evidence for it whatsoever. The comet passed through, in a manner of speaking, without leaving a single legible word in any dataset. This outcome is perhaps the most frustrating from a human perspective, because it forecloses even the possibility of a future discovery. In the ambiguous scenario, there is always the chance that someone revisits the data with better models or more sophisticated analysis tools and find something that was always there, waiting. In a true null result, there is nothing to find. The signal was either never coherent enough to detect at this distance, or was so thoroughly overwhelmed by background noise that it is mathematically irretrievable. Either way, the chapter closes without resolution. A third possibility, less likely than the first two but genuinely not remote, is that one or more spacecraft captures what scientists would call a tentative anomaly. Something that, when you look at it carefully, has some of the characteristics you would expect from a tail crossing. The magnetic field rotation is not textbook perfect, but it has the right general shape. The density shows a slight decrease around the predicted crossing time, within the margin of what the models suggest. The composition data from ACE shows something mildly unusual in the charge state distribution of heavy ions. Not definitively anomalous, but worth flagging. Nothing individually compelling, nothing that would survive as a standalone detection claim. But several things, pointing in roughly the same direction, occurring around the predicted time. This is actually the most scientifically interesting short-term outcome, not because it is the most satisfying it is not, but because it generates a research thread. A team of scientists notices the anomalous cluster of marginal signals. They decide it is worth a closer look. They pull the full composition dataset from ACE and spend several weeks doing the careful charge state analysis. They compare the stereo A data against the L1 data and check whether the anomalies appear at both spacecraft in the geometric sequence the tail crossing models would predict. They build a case, slowly, with explicit uncertainties attached to every step, and eventually they write a paper framing the event as a possible detection of PANSTARRS ion tail, stressing the word possible, quantifying the uncertainty, describing the alternative explanations they considered, and why they find them less convincing but not impossible. That paper, if it gets written, takes time. Heliophysics peer review is not a rapid process under the best circumstances, and a detection claim of this nature, rare, contested, dependent on subtle multi-instrument correlations against a complex background, will face rigorous scrutiny. Reviewers will push back on the analysis methodology. They will ask for additional corrections, additional comparisons, additional tests of the alternative explanations. The authors will revise. There may be a second paper from a different group reaching a different conclusion, or at least a more cautious framing of the same evidence. The back and forth of scientific debate in the literature is slow, sometimes frustrating, and almost never resolves cleanly into a single definitive answer on the first pass. Anyone sitting refreshing a newsfeed on April 26th looking for a press release confirming that Earth-crossed PANSTARRS tail is going to be disappointed. That is not how any of this works, and it is worth saying so plainly rather than allowing the timeline expectations to get inflated by the drama of the 47-hour window framing. The window closes, the data gets archived, the scientists go back to their other work, and the interesting analysis begins quietly, on timescales that have nothing to do with the news cycle. Then there is the genuinely exciting possibility. The one that would be unambiguous, that would not require months of careful argument building, that would show up in the data clearly enough that multiple instrument teams independently notice something unusual in the same time window. A clean interplanetary magnetic field rotation with the hairpin profile of magnetic draping. A proton density decrease of 20% or more, lasting several hours, symmetric around a central minimum. A simultaneous anomaly in the ACE composition data showing low-charge state heavy ions inconsistent with any solar wind source. Stereo A seeing a consistent signal at the geometrically predicted time offset. All four indicators, multiple spacecraft, unambiguous enough that the scientists watching in real time actually say, out loud to each other, that might be it. This outcome is the rarest of the realistic scenarios. Not impossible, the geometry permits it, the physics allows it, and if the tail happens to be more coherent and more dense at Earth's crossing point than the conservative models predict, it could happen. But the concurrent solar weather conditions make it the least likely of the near-term outcomes. The coronal hole stream is too loud, the active region is too active, the noise floor is too high. The signal would need to be significantly larger than current models expect in order to stand clearly above everything else arriving simultaneously. What the scientific community's working posture actually looks like, based on the informal discussions and pre-event thinking that surrounds events like this, is something like this. Watch the data carefully, flag anything that looks interesting, preserve everything meticulously, and do not expect resolution on a 48-hour timescale. Expect resolution, if it comes, on a 6 to 12-month timescale, maybe longer. The Hyakutake crossing took 4 years to emerge from the archive. This one might take 2, it might take 5, it might never emerge at all. That is what the science actually looks like from the inside. Not a drama of real-time revelation, not a countdown clock with a definitive answer waiting at 0. A slow, methodical, sometimes maddening excavation of a very noisy dataset in search of a very quiet signal, conducted by people who are comfortable with uncertainty in a way that most science communication is not, because most science communication wants a conclusion, and this story may not have one for a very long time, which, if you think about it, is exactly what makes it worth following. The window closes on April 26th. The real story starts the morning after. Part 20. The real ending. Delayed discovery. Here is the actual timeline of how this story most likely ends. In the days immediately following April 26th, nothing obvious will have been reported. The CHHSS will have swept past Earth, leaving behind the usual residual geomagnetic effects. Space weather conditions will gradually settle back toward baseline. The data from ACE, DSCOVR, and Stereo A will be archived and available for download. PANSTARRS' perihelion passage will recede into the past. The comet will begin its long journey back outward to the cold outer solar system, not to return for centuries or millennia. The window will have closed. In the weeks following the window, a few researchers who were specifically watching for a tail signature will go through the data carefully. They will find, in all likelihood, a dataset that is dominated by the coronal hole stream and the associated geomagnetic activity. They will flag 1, maybe 2, time periods where the data has some character that might be consistent with a tail crossing. They will note the uncertainties and begin the process of trying to characterize those anomalies more rigorously. In the months following, the analysis deepens. The composition data from ACE gets carefully corrected for the solar wind background, using models of what the CHH-SS elemental fractionation pattern should look like based on the source region properties. Subtracted from that background, a residual may emerge, a slight excess of certain ion types that does not fit the solar wind model as cleanly as everything else. Or it may not emerge. The models may fit the data perfectly, leaving no residual attributable to anything external. If a residual does emerge, the Stereo A data gets consulted. Does the anomaly appear there too at the time predicted by the orbital geometry? Does it have the right character? Does the magnetic data show any hint of a rotation consistent with draping? This multi-dataset correlation is the key analytical step, and it is the step that will take the longest, because it requires careful work from multiple instrument teams who may have slightly different calibration assumptions and analysis methodologies. A paper takes shape, cautious in its claims, careful in its uncertainty quantification, framed explicitly as a detection attempt rather than a confirmed detection unless the evidence is genuinely strong. It goes through peer review. Reviewers push back on the interpretation. The authors revise. Perhaps a second paper from a different group arrives at a different conclusion. A small scientific discussion develops in the pages of journals most people will never read. And at some point, maybe a year from now, maybe 3 years from now, the community reaches a working consensus. Either PANSTARRS' tail was detected, a modest detection, uncertain but probable, archived as a companion case to Hyakutake, or it was not detected, the conditions were too noisy, and the event joins the much longer list of predicted tail crossings that produced no confirmed signal. Both outcomes are scientifically useful. A detection adds a second data point to a dataset that currently has only 1, and 2 data points are immeasurably more valuable than 1 for building any kind of physical model. A non-detection establishes a constraint on tail density and coherence at these distances, which is itself informative. Science advances on null results as readily as on positive ones, even if null results attract fewer headlines. This is how it actually works, not with a flash of revelation on April 26th, not with a press release confirming that Earth passed through a comet's tail and here is exactly what happened, but with a slow, grinding, multi-year process of data collection, analysis, uncertainty quantification, peer disagreement, revision, and eventual provisional consensus. The dramatic moment was invisible. The drama of the discovery is entirely intellectual, played out in papers and conference presentations and quiet arguments over methodology. The Ulysses Hyakutake story took 4 years to emerge from the data. 4 years from a crossing in 1996 to a paper in 2000. And when it did emerge, it was extraordinary. Not because of what it told us about that specific event, though that was interesting, but because of what it told us about what is possible, about how far a comet's influence can extend, about the kinds of structures that exist in interplanetary space that we cannot see but can measure, about the way the solar system is woven together with invisible threads of magnetic force and ionized gas that extend across hundreds of millions of kilometers. PANSTARRS may or may not add its chapter to that story. The geometry was right, the comet was active, the instruments were in place. Whether the noise of the universe chose to cooperate is another matter, and the universe, as a rule, does not consult anyone's preferences about signal-to-noise ratios. But here is what stays with you, or at least stays with me, when you think about what this week actually represents. Somewhere in the data being collected right now, in the streams of numbers flowing from ACE and DSCOVR and Stereo A, recorded to drives that will sit in archives for years, there may be the faintest trace of a comet that formed in the cold outer solar system billions of years ago, swung into the inner solar system for the first time in recorded human history, passed inside Mercury's orbit for a brief fiery moment, and left behind a ghost of ionized molecules that drifted outward at the speed of the solar wind, and then, for 48 hours in late April of 2026, swept over a small blue planet that had instruments sensitive enough, barely to notice. Maybe, or maybe not. The data will decide. Not the alignment, not the narrative, not the striking convergence of 5 events into 1 week that our pattern-seeking brains want so badly to make meaningful, just the data. And the most profound thing about that, the data does not care about the story, it just is what it is. The signal was there or it was not. And somewhere between the noise and the archive, between the real event and the delayed discovery, between what happened and what we will eventually know, is the exact place where science lives. That place is not glamorous. It is not dramatic in the way a fireball in the sky is dramatic. But it is where understanding actually comes from. And if this story ends the way the Hyakutake story ended, with someone years from now pulling up the April 24th through 26th data set and suddenly seeing something in the numbers that nobody was looking for, then the drama was there all along. We just had to wait to be able to read it. The signal, if it exists, will not be seen in the sky. It will be found in the data we almost ignored.